again. Oh, I love VIF. Let's do some VIF. Now, VIF, variance inflation factor. So every question people ask is 100 points if I start talking through it. So we'll do it with Lauren's here, then we'll go to Preston's. And this is mainly driven by you guys, so thank you for being here, keeping asking those questions, and I'll go through it. I'm gonna lightly close my door just in case I have worse still people around. So I'll be right here, guys. So I'm just gonna lightly close my door so that way people are walking by. Okay, let's do some variance inflation factor. What is variance inflation factor? Well, variance inflation factor is something in multiple regression. So what we need to do is we need to go here, and let's just call this multiple regression model. It doesn't matter what we call it. We're gonna make, let's go to survey 10. What you're gonna see here is, do I have this open right now? I don't. So I'll look at the chat one second. Dply. Is nothing running today for me? Am I losing my mind? Do I not know how to spell dplyr? Is right class here? Oh, I don't know how to spell library. There we go. Okay, cool. I don't know how to spell anything. And I don't have my data sets loaded up. So let's go to data survey 10. I might not even have right class on. Let's find out. I don't have right class on. It's kind of good. Okay, library, right class. Reg class is now on. Survey 10 will be available once reg class loads in here. So data survey 10, I love survey 10. And what we're gonna do is we're gonna grab, so let's put a hashtag. Let's do install.packages dplyr. I'm gonna post this afterwards and this video will be posted. So let's put this right here as a code before this. So you can follow along. Remember, I am posting this and focus more. So let me read. Hello, Brian. Could we look at an example of best polynomial for predicting two things using X? Sure. We haven't done polynomial a lot, so we're not gonna. We'll show some because that's on the take home. There's gonna be bonus on the take home, as long as you guys like bonus. What are the best things we need to know for the midterm? Lots of things like this. Like other changes could interpretation outside of otherwise identical. We'll go back to interpretation here. We'll go through VIF and then we'll hop from topic to topic. And let's do this. Let's put a timestamp in here. And let's do a timestamp on the VIF. So this is VIF at 5:08. So we're just putting a timestamp right there so people can kind of go through the video at about 8 minutes in. And we'll definitely be doing all of these. Ooh, I like that. Victoria, great question. So to make this right here, we're gonna do cool. Let's grab some variables right here. And why not? We'll do desired weight plus weight plus GPA. And these are my X's. And let's talk about what we have right here and what it all means. So I'm making a multiple regression model. And I'm putting my X's first, and I want you guys to tell me where you think there'll be high variance inflation. And remember, I like the conceptual stuff. I really like if you guys understand the concepts behind this, because the math's one thing. When we use these things in business application, people are not gonna be doing all the math. We're not gonna work the math by hand. We're actually gonna talk through what this means. And so where do you think the high variance inflation factor will be and why? I feel like I should, now my brain is on test questions, and I think this would be a great one. Just looking at that code, you should maybe suspect some high variance inflation somewhere. Where would there be high variance inflation? Remember, I need you guys to answer some questions, and then it'll help me come up with even more. But where would there be high variance inflation and why? And I'll probably start answering it in a second myself. But think about where there'd be high variance inflation. Well, what variance inflation is it's due to multicollinearity. There's a keyword you should know. Multicollinearity is when the X's explain the X's. We do not want our X's to explain our X's. So you're actually looking at the relationship of these variables. You'd have to ask yourself, is desired weight explained by these? Is weight explained by these? Is GPA explained by these? Is text per day explained by these? Desired weight and weight might have a high variance inflation factor, exactly. And because they're explained by each other, and it's also how the other ones explain it too, because it's, and so Alden, I think it's correct. Alden, you are correct. And Lauren, you are correct, 50 points. Every correct answer tonight, 50 points. Just keep track of it and get a ton of points tonight. But desired weight and weight are probably gonna have a high variance inflation. It's because I suspect that they share sources of variation. And if you notice, they do have the highest variance inflation. What they bring to the model is not unique. You could say, well, is somebody's weight their desired weight? No, it's not. That's why they're different. but they're redundant. Preston, that is exactly right there. Preston, 50 points. That's perfectly what I want to hear, is that they contain in them redundant information. And the multicollinearity would be due to the way desired weight is explained by weight, GPA, and text per day. So when you look at the multicollinearity of desired weight, it's how is desired weight explained by these three. The multicollinearity of weight is how is weight explained by these three. The multicollinearity of GPA is how is GPA explained by those other three. So you can come up with different multicollinearities right there. So this is how multicollinearity works. We don't want there to be redundant information because that creates variance inflation. And so we always want low VIFs because that means that the variables aren't redundant. Yeah, that's a good thing. And as we saw in our last assignment, and I have talked to the grader, and she said that she's been pushing back when things will get graded, but originally it was Friday and then it was Sunday. And I know the assignment 4 is graded, but assignment 5 and 6 should be graded soon. I'm very sorry. And she said she's not going to fall behind again. I'll be speaking about that in class tomorrow, just so everyone knows personally that I have been aware that we got 3 weeks behind on the grading. When it hit 2 weeks, I was a little concerned. When it hit 3, I was definitely like, we need to fix this. And she said she's not going to get behind after this. So my apologies for that, but I have been aware of that and making sure we try to stay back on track. So right here, we see that we have desired weight has a variance inflation of 4. Now, I want us to think for a moment about how much is the standard deviation inflated if the variance inflation is 2. If the variance inflation is 4. You guys should know the answer now. I'm not trying to give them away, but apparently I am. Approximately 2, approximately 2. And how did you find 2 and why is it 2? Because remember, variance inflation is squared of standard error. So you can square the standard error and get variance, or square root the variance inflation to get about what the standard error is inflated. So when we look at our model right here, what we would have is the estimate, or the uncertainty, which is the standard error right here for desired weight, has been effectively doubled. But wow, look at that. Look at that p-value or t-statistic. You can tell, and we'll talk about this output here for a second. We'll kind of jump a topic because we kind of talk about what variance inflation is. And variance inflation does not invalidate a model. It just means that your x's share overlapping variation with each other. The overlapping variation your x's share with each other is the what? Like, what is the term for the overlapping variation that your x's share in some sort of combination with each other? That term is what? The overlapping variation that your x's share with each other is known as multicollinearity. So if you're typing multicollinearity, definitely type it out. Multicollinearity, and it's because between 2 x's, it's collinearity, but between multiple x's, how one x is explained by like a bunch of x's is multicollinearity. And then multicollinearity leads to variance inflation. So what is it's like the illness is multicollinearity. And then what we get from multicollinearity is variance inflation. Variance inflation is the extra uncertainty we have. So this number right here has been inflated. Actually, all these, well, this number and these 2 numbers are the most inflated due to multicollinearity. And it is variance inflation. I wish they just called it standard error inflation. It would make our lives easier. But when they came up with it, they called it variance inflation. But variance is in squared units. So we don't really talk about variance inflation much because we don't want to talk about squared units of our variables. So we just talk about just regular old standard error. And we get that by doing the square root. So this number here, to our best estimates, has been effectively doubled. And why does that hurt us? I do like theory questions on this, and it's even making me think of more test questions as we go through this. Like, what is this number used for? And we're kind of going into this output, which I do want you guys to know how to read this output. This number here is your uncertainty in this estimate. You're right, it's our uncertainty. So you're saying you're doubling your uncertainty, Elijah. Definitely 50 points right there, congrats. You have doubled your uncertainty in this number. This is like me saying, it'll cost $13.64. But the problem is I have uncertainty. It's like, how much do you think that'll cost? $13.64. Here's my uncertainty. Is uncertainty in pretty much anywhere, is uncertainty ever a good thing? Pretty much no. Uncertainty is never a good thing. So when we have high variance inflation, we increase our uncertainty, and that'll make our intervals wider. And if our intervals are wider, they might contain what? If our intervals are wider, they might contain 0. And if our intervals for an estimate contain 0, then the interval would be what? If the intervals for our estimate contain 0, they would not be statistically significant. And be careful, this is an interval for an estimate because we're doing estimates for the model. We don't want the estimate for the model to be 0 because then we're saying this thing doesn't matter. It doesn't play a role in explaining this y. It's not an important variable. It has no impact. And remember, we do have some right here. If you were to make a confidence interval for this, you can see pretty quickly that these hit 0, just if you do plus or minus 2 standard errors. Try this out, put it in the chat. I'll throw 1,000 points first person to get it. Make a 95% confidence interval for the GPA. And I'll take this question right here. So do this, and so try this in the chat. I do like questions like this. Make a 95% confidence interval for the coefficient of GPA using this information. Make a 95% confidence interval for the coefficient of GPA. Try it on your calculator. It's a good kind of example question. And I know people like, Brian, what is a test question going to look like? I like this one a lot. I just throw it on the test all the time, like make a 95% confidence interval for the coefficient of GPA. And does that make it inclusive, or is that only for p-values? This is a confidence interval for the coefficient. A confidence interval for the p-value, we talk about conclusive or inconclusive. So Victoria, good question. If we're doing a confidence interval for the p-value, that's when we state that the confidence interval is conclusive or inconclusive, whether or not it has 0.05. So make sure to have a good note when you're studying or on your cheat sheet that confidence intervals for p-values, we care about 0.05. If 0.05 is in the interval, it is inconclusive. If 0.05 is out of the interval, it's conclusive. And then if it's below 0.05, then it's significant. And if it's above 0.05, it's insignificant. So, and does anyone have our confidence interval? What would you do? I think you got it right, Alden, but Alden, you're really close. Oh, no, you do. I just missed Alden. You're exactly right. Alden, thank you very much. And I wonder if, I'm gonna try something here. If I get this right, if I know how to do this, then something is firing in my brain that's not usually firing. Wow. Oh, wait. Alden, I think, oh, I made a 68% confidence roll, so I did it, but I didn't do it. There we go, right there, Alden. So it's Alden, right? Am I saying it correctly? And yeah. And you might have done it more exactly, and remember, don't cheat and use confident yet, because you might not have that output on the test. We could cheat and use confident right here, and this is the more exact. So if you notice here, a 95% confidence roll is plus or minus 2 standard errors. It's not exactly, but for all intents and purposes, whenever you're estimating stuff, unless you have some small sample size, you can usually just go plus or minus 2 standard errors. So there is the whole issue of small sample size, which we just shouldn't forget. But in most cases, a 95% confidence roll is well estimated by plus or minus 2 standard errors. Very, very commonly used to just go plus or minus 2. So does everyone see how I did that mathematically? You can see my math right here. Just take the estimate and go plus or minus 2 standard errors. I did 1 or 2 in these in class, but it's pretty quick. All you're doing is taking your estimate and go plus or minus 2 standard errors. Does that make sense to everybody who sees my math right here and sees how this interval right here is very similar? It's pretty accurate to the first and second decimal on it. So it's a pretty good and quick way to just say plus or minus 2 standard errors. So does everyone see that right there? Does that make sense? Cool. All right, so remember, a confidence roll, especially 95% one, is plus or minus 2 standard errors. All I did was take my estimate and then my uncertainty. So it's just 2 uncertainties. I just go out like that. I just say, well, here's my estimate, 2 uncertainties. A lot of great questions have been brought up here. Let's put a timestamp on that. Let's do confidence intervals. Confidence intervals 518 or so. I guess you could look like in the video as you watch, like what we saw. Let's go to associate function. Do like some associate output. I can't type the C right now. Associate output. So get my associate. One try. There we go. And let's do the associate function because this is some old school stuff we haven't done in a while. Gender's fun. Okay, I think gender's in this one. Is gender? Let's just use an obvious one. Let's go gender and height. This is very obvious. We'll just do something crazy obvious to start out with. And please ask questions when you have it. Okay, so I'm gonna move this. Well, you don't see it in the video, but we'll double check. Okay, so here we go. We want to know, and I don't know if I picked this example for the test. I'll explain why. Why, now when we analyze heights, we would either compare what or what. And we have two different measures of central tendency. You might hear me call it central tendency, but that's the global catch-all term for either we're going to use blanks or blanks to analyze this. So when I analyze heights between males and females, oh yeah, Victoria, another 50. Great job. You guys are so good in the chat. So it's just the measure of center. Like, how are we defining the center? By the average or the median? So you're exactly right. Now, one of these is definitely mean. Which distribution is definitely means? The distribution of which ones is, there's no question. I would use means on it. And where do you see that? You should see something in here like, yeah, that one's pretty normal. And I'll hover it over in a second. But you should look at this output. Here's where I like to pause, and let me put in a timestamp here too. So let's go here and go to hashtag talk about means and medians. So what output are you looking at right now to figure out if you should look at means or medians? What output are you looking at right now? QQ plots, right down here, we're looking at these QQ plots. Which of these looks like it's definitely means? Like if both of them looked like that, it'd be means. Which of these looks like the males? Look at that, that's following it really well. Where the females has this, I like to make them pretty obvious. And one thing I like, I'm totally giving away my tricks here. I can't remember which one I did on the test. This is not me trying to double trick you or anything like that. But I like it when it's means, because then a lot of people think you need to use this output right here. These are the permutations down here. All this down here is your permutation results, like the ones that are created by random chance, with your result right here, and then the permutation results here, and the p-value on this one's basically 0 as far as we can tell. But this one right here looks a little weird because there's this little blip down here, but you really want to analyze the QQ plot. And from what we can see, the QQ plots, there's some issue. I mean, the males are means, but females have I don't like this as a test question. If I were to personally do this one, I would probably use means. There's some outliers down here. It's not, look at most of the shape is unimodal symmetric, and that's what we want to see with means. I wouldn't use this as a test question. I'm gonna make it more obvious. I'm gonna put all the points pretty much inside or make it like crazy. So I'm not gonna go for something that, I've already made this question, so not that this is on the test. But mine's obvious on the test because I want things to be obvious if we're doing a test on it. So once again, we're gonna say, I'm gonna say means, but I don't like it as a test question because men look really good and normal. Females have a little bit of a problem. I'd probably give this a C. And a lot of people might not like that C. That's really bordering on I don't like it, but I'm gonna go ahead and use means. Now that I'm using means, I'm gonna go back here to this output. Now I want you to tell me the practical significance between males and females with the measure I've chosen. What is the practical significance? And kind of give me it in context. Try writing a sentence about the practical significance between males and females with the metric I've chosen. Just pretend it's a homework question. So what would you do here to talk about the practical significance between males and females with the metric I've chosen? Well, first, you need to figure out what the metric is that I've chosen. So we chose means. So then you need to tell me about the difference between the means of men and women. Tell me about that. Go ahead and try it right now. Have your calculator out, have it open, try to solve it. It's really easy to figure out the median difference. You just look down there and say 7. And I'll do the medians for you guys while you type out some sentences for me with the mean. But we see here that the 50th percentile of males are 6 feet tall, where the 50th percentile of women are 5'5". This is a difference of 7 inches between the median heights of males and the median heights of females. So does everyone see what I did right there? Is I took the two numbers and I talked about the difference. Now, is more than half a foot a pretty large difference in terms of height? Does that seem practically significant in terms of height differences between males and females? I guess half a foot, that's none. The difference between men and women on average is approximately 5.44. Maybe, I'm trying to think if that's right. Might be right. Let's find out. Might be right. Maybe it is. 6.44. I was like, I thought that looked like 6. That's why I was. So if you notice, just subtracting, let's hashtag. There we go. No worries. You're fine, Harry. You're fine. I'm throwing you 100 points for that. I appreciate it. I want all the answers I can get. I work off of answers, so don't worry about it. I was like, it looked like 6 to me, but oh, you guys just seen I was making so many mistakes with stat to 1. Just, you know, your head just goes and you just flip an answer. So this is, I would say, the difference between males and females on average is about 6.44 inches, where males are about this much taller. That's a half a foot. That's a lot. That seems like a practical significance. So let's kind of go through some of our steps right here. It does depend on the situation, because half a foot, let's say these were buildings, and we're talking about buildings in New York versus buildings in like San Francisco, and we find the average height of buildings. And this is like New York buildings and San Francisco buildings. And these are, they have a difference of this many in their inches. There's a difference between like, and it's statistically significant, but the buildings in New York are half a foot taller, or 6.44 inches taller. And I know the buildings aren't really, you know, like 5'10" or something like that. But if the difference between buildings in New York and San Francisco was half a foot, would that be practically significant? It would not be practically significant. So it would still be the same difference. You notice how I'm saying the difference between the average height of a New York building and the average height of a San Francisco building is 6.44 inches. But in that instance, we're like, well, who cares? That's half a foot when it comes to a building. And someone's like, no, 6.44. But even when it comes to heights in males and female, half an inch, like if you have an NBA player and they're 6'10" or 6'10.5", it's like, it's got the, no, it helps. It's a extra half inch. So in buildings, we wouldn't care about this difference. And then in humans, this would be a sizable difference to say this group of humans is 6.44 inches taller on average than this group of humans. So the context matters. Every time you do practical significance, you have to think about, you really have to pause and say, do I care about that? Which I know can be one of the hardest things, because it just sounds crazy. It's like, in these questions, there is no right or wrong answer, because someone could be like, oh, I don't care. But I think with this one, I try to make it as obvious as possible. And that's why I chose this one, because I knew it would come out ridiculous. The median interpretation was, there is a difference in the 50th percentile of male heights and the 50th percentile of female heights of 7 inches, where the 50th percentile of males is 7 inches taller than the 50th percentile of women. And so that's key right there. Medians is 50th percentile. The 50th percentile of males is 7 inches taller than the 50th percentile of women. So that's the difference in the medians right there. Where we see the difference between the means of men and women is that the mean for men is 6.44 inches taller than the mean for women. Both of those I do find to be practically significant. And are both of these statistically significant? Are both of those statistically significant? Most definitely. I'll go to that question in 2 seconds. And let me go to it right now. Outside of knowing that the x variable explains, what is a good way to figure out what variable is your y and what variable is your x? Good question. No, Preston, great question. One, on the test, I'm actually going to show you. I've got the test over here. We're not going to go over to it, but the test is right over there, and I actually show you the code that makes the output. So you'll actually get to see. So for those who like coding, and maybe you do, maybe you don't. It's funny. Everyone's like, a lot of people are like, oh, I like the coding more than the interpretation. I don't know. I like the coding too. But for those who really like the coding, you'll get to see all the code I used to make it. So if you're wondering what was the y or what was the x, you'll really get to see it on the thing. Also, please ask any questions during the test. I've had some classes where teachers are like, no questions. And I'm like, no one writes perfect tests. I don't write perfect tests. There'll probably be a typo on the test somewhere. I've had a few that are good, like there's no typos. But so please ask a question if you have it. I'll happily answer. And if there's major questions, like if someone notices something major, I'll announce it to the class. So I try to make the test as best I can, but I'm better at math than I am English. So to decide which central tendency to use, we look at the QQ plot. Exactly. If the QQ plot follows the red line, it's hard to see where that red line is at. Well, you can see it right there because it's not following it. The more the QQ plot follows the red line, the more it is means, because this is the normal curve on the red line. The less it follows it, the more it is medians. So for non-normal data, you use medians, and for normal data, you use means. Yes, I think so. Nice job, Alvin. Nice job. So right here, let's think about what else. Okay, so what numbers here tell us that our results are statistically significant? And I'm gonna ask as many questions as I can. I'm just like, people hate oral exams, but I think they're great. It's just like, I wanna ask you guys as many questions as I can to see if you can get like what numbers would I use to analyze the statistical significance of these results? How can I tell if my results are statistically significant? Close-ish. This is not an ANOVA. Well, actually, it can be. So Elijah, I'm throwing you 100 points because we can use an ANOVA for this. We can, but we won't. Sorry, we can. But we're going to look at the p-value on the test. So we could use an ANOVA technically because we could do an analysis of variance between the means between each group. So we can. Or we could even use a t-test. There's a lot of ways to do this one. So the short answer is p-value. Then it would come down to are you using a t-test or ANOVA. And for two groups, which this is, the t-test and the ANOVA would come to the same conclusion. T is f is t squared. Anyways, enough of that. Right here, these p-values right here, the p-value for the averages is statistically significant. And this one right here, basically I'm trying to illustrate to you by clicking on these that these are your p-values to tell for statistical significance. Are my results conclusive? And you can tell me about either one. Are my results conclusive for these? And why? Are my results conclusive and why? Yes, it does not contain 0.05. If you notice, I like that we did this one next, is kind of why I picked it, because I switched the topic. I'm no longer looking at, my brain's like shutting down. I'm no longer looking at whether or not my interval contains 0, because I'm not doing estimates for my model. I'm doing intervals for the p-values. So with it being intervals for the p-values, I'm looking to see if my interval contains 0.05, because we're looking to see if 0.05 is an interval, because that would be a bad p-value. Be careful when you look at a confidence interval in this test. Say, is that a confidence interval for the estimate in a model? Oh wait, this is like a linear model, and so I don't want my estimates for my coefficients to be 0. Or look at another one and say, wait, this one, which we're looking at now, is a confidence interval for the p-value of a model. I don't want my p-values to be 0.05 because that's where I'm like, I don't know if it's statistically significant. So this is a conclusive interval with significant p-values. So it's conclusive because the interval I have highlighted does not contain 0.05, and it could be above or below, but it should not contain 0.05. If it does not contain 0.05, that interval is conclusive. So this is this output right here. I think we've talked through it. We could just do a little switcheroo right here. Cool. That's how quickly, oh, no. Well, let's do this. Let's go ahead and switch it. No, let's copy it. Let's bring that back and let's go here. And let's talk about some correlation. Okay, 5:33. I'm doing the time on it. Talk about correlation. Do you know that it is a p-value confidence interval because it's a permutation? Kind of. We can do confidence intervals for other stuff. Yes-ish. I would look, and I would look at this right here. You see how it says the p-value? This is another p-value. We use a lot of these for, a lot of the p-value confidence intervals are based on permutations. So I want to say almost pretty much yes in this class, but I wouldn't put that as a thing for everything. The reason I know it's a confidence interval for the p-value is it says the p-value for the Pearson correlation is contained in the interval blank to blank. You see it says I am 95% confident. We are 95% confident that the p-value for the correlation is contained in blah, blah, blah. And then right here it says we are 95% confident that. So I know it's a confidence interval because we are 95% confident that the p-value of the ANOVA means ANOVA is contained in the interval blank to blank. I usually say contained. So I've always said it before. But if you notice here, we are 95% confident that the p-value, and I just said no to the ANOVA a second ago. I'm sorry, it was ANOVA. Yes, it is. And then I corrected myself kind of. But Elijah, I'm throwing you another 100 points. Thank you, Elijah. Thank you, Elijah. I shouldn't say no to students when they're right. Like, you are right. So I was thinking it's the association test, which runs in ANOVA for us. And I was also thinking ANOVA and regression. So my brain twisted for a moment. But with this in mind right here, wow, okay. Now there's a lot of metrics to look on this one. Do you think we should use, well, there's two choices we should make when we look at correlation. Looking at correlation here, we choose between blank or blank with the correlation. What two things will we pick from the correlation? What would we pick? What are our two correlations? What are those two correlations? Spearman or Pearson? And why would we pick Spearman? Why would we pick Pearson? And someone one time showed me, they said that the P in Pearson kind of got that, look at that P in Pearson. We kind of turn that P this way. P in Pearson kind of, what is it all about? Preston, I'm Preston, 100 points. Spearmint is for monotonic nonlinear. So Spearmint can handle a lot of things. Let's think about 3 things it can handle. The 3 things Spearmint can handle are outliers. It can also handle nonlinearity. It can also handle what for 100 points? What's the 3rd thing it can handle? One of my favorite words. You know what word I'm thinking of. I don't care how you spell it. Don't worry. Just start typing it. I'll type it. Oh, they already got it. I was going to spell it all crazy. Like, you got that heteroskedasticity. I like it. Elijah and Preston, 100 points. You both. I like that, Elijah, right there. So heteroskedasticity, fun word to say. Look at our plot over there on the right. I definitely see, what do you see? There's a few things that jump out to me. Do you see the outlier right here? Do you see an outlier over here? Also, what's this kind of really illustrating that this is a, if you notice, I'm still going up, but I'm kind of bending at the end. Yeah, that's a curve. That's, oh, this is Spearmint 100%. This is total Spearmint. And just look over here. This is not really, you wouldn't look at your estimates and be like, oh, Pearson's lower than Spearmint, but Pearson does a better job. It's because this is a candidate for Spearmint. They're both, is there a linear relationship to this to some degree? Is there some linear relationship to this? Yes, that's why the Pearson is picking up on it. But what is the stronger relationship? And that is the one that is closer to -1 or 1. And the stronger relationship is when we look at the ranks. So we'd rank every number, and then we'd look at the rank correlation, the correlation between the ranks, and it's a much stronger rank correlation. So Spearmint better explains relationships that are nonlinear but still monotonic, heteroskedastic, and have outliers. Like, those are the things, if you start to see those symptoms, you're really like, it's bordering on Spearmint right there. That's some Spearmint. And if I saw this plot, and that's what you want to get the eye for, is to be like, okay, wait, this has got some outliers. That's got some pretty strong nonlinearity. Maybe heteroskedasticity is the least of my concerns for this one. So but it's got the other 2. It's got 2 out of 3 pretty strong. And so I'm going to say this is definitely a Spearmint relationship. Same sort of thing going on here with the p-values. How do we know it's statistically significant? Look at that p-value, boom. And probably we should look at the Spearmint because that's the one we decided on. Spearmint is statistically significant. And then I'm just knocking my cord everywhere underneath my feet. Spearmint is statistically significant. Then what does this tell us right here? My conclusion about it being statistically significant is what? My conclusion about it being statistically significant is conclusive because the interval does not contain 0.05. But what if, hypothetically, that interval was... Oh, no, I don't want to do that one. If my interval was this for the p-value, would that be conclusive? It is conclusive because it doesn't contain 0.05. What do you think the p-value was? What do you think up here the p-value would say if that was the interval? If that was the interval, what do you think the p-value would say? Well, how do you think we make our interval for the p-value? This is the answer. Here's the interval. Here's the p-value right here. You got it right. Victoria, 100 points right there. First one to answer. Great job. Because it's just at the center of the interval. Does that make sense? It's like, it doesn't have to be the way we do the permutation procedure. It would look at the permutations and find out from so many permutations what was the p-value, and it would take, but usually you get that sort of symmetric interval around it. It's very common like that because it's like, well, we're going to look at, the best estimate of the p-value would be from the permutations we do, what results we get. But then when we look at the permutations, we can say like what would have happened and other results. So yeah, that's excellent right there. I think, do you guys remember, we spent like a whole week doing this. I mean, how much, I guess we got to build up everything. Do you guys feel like correlation's pretty easy? Do you feel like you got this topic? If we were to talk about here the practical significance of this, could you handle some practical significance on it? I mean, what would you do? What would you write me for practical significance on this? Shouldn't tap things. That'll come out loud in the review. Dr. Peach sending me tips for my review tonight. The practical significance of this would be based on the correlation. So if you're looking for practical significance with only the numbers you have right here, it'd be on the correlation. And definitely I would say that you think about that, that's an R squared of at least like 40%. We could square it and get R squared. And this would be the percent of variation explained by the rank of Y due to the rank of X. I didn't put this on the test, don't worry. But 45% of the variation in the rank of y is explained by the rank of x. That is not on the test, because you can square r squared and get the percent of variation in y explained by x. But remember, this is how the rank of x explains the rank of y. That's not on the test. But it seems to me, at least, that having that much variation explained, that it's around 50%, a little less than 50%, and that's usually the way we would talk if we were in a meeting. We'd say a little less than 50% of the variation in the rank of y is explained by the rank of x. And I could say it in terms of the actual problem, a little less than 50% of the variation in the rank of height is explained by the rank of somebody's weight. So if you notice, I turned it into an r squared. We'll start bridging the gap into regression here in a moment. How about we do some correlation? I need to put these markers out of my reach. There aren't three reasons we really use Pearson. Pearson is when it's just like linear, well described by a line. And then we have our three reasons we really would go to Spearman. So the reasons we use Spearman are the reasons we don't use Pearson. So the three reasons are heteroscedastic, nonlinearity, and outliers. Heteroscedastic, nonlinearity, and outliers, which this one shows a lot of symptoms of. No, good question, Lucas. 100 points. Thanks for asking that. Wait, what was the 0.75 again? I blanked out. No worries. That's where I made up a fake question right here, and I asked, what is the center of this interval? So I asked, what's the center? And let's put center of p-value interval. It's just the middle of the interval. Can you just look at all the ranks from the output and pick the higher number to know which one to use between? I wouldn't suggest that. It's not the worst thing in the world. You know, it's probably not the way I wrote the test question, but you will often see that if something's better described by Spearman, so knowing where the problems with Pearson are, that it doesn't do well with nonlinear, heteroscedastic, or outliers in data. So then that's usually where you switch to Spearman. You could look at some correlation values to see which one is working better. It's not like a horrible thing to do, but kind of knowing why we use each one and when it's good too, especially for our test. Because sometimes we talk like real world. If we're just out there, we might just like run some values and figure out what they all are. So then let's switch. Let's do another association function right here. We need some, let me look at that glimpse again, look at the data. Oh no, wait, what is glimpse doing? Glimpse is supposed to be the one that doesn't make mistakes. Glimpse, really? What you doing, glimpse? There we go. It's supposed to not wrap the screen like that. That's weird. It's the first time I've ever seen it wrap. We've got here handedness. Let's do handedness and gender. So we've got here gender and handedness. And let's go here and put in a time code again. Talk about mosaic and contingency table. Probably misspelled that. And what time is it? It is 5:43. You're welcome. Thank you to everyone for being here and especially talking in the chat. Keeps me going, keeps me thinking. Let's take a look at what we have going on right here. You can tell what's going on. I picked two kind of counter examples. And actually for once we get to see that permutation test. For once it's not actually off the screen. So let's take a look at these results. We got here the mosaic plot. We got the ambidextrous people. We got the left-handed people. We got the right-handed people. We got the females. We got the males. We can zoom in on this, make it look a little bit bigger right here. For the in-class test, we have questions about what you put into the commands while coding. I've only written one question on that, and it's pretty simple. I think it's worth 2 or 3 points on the test. Very, very simple question. Should be pretty easy. Maybe I'll find a way to do it tonight. I think don't worry. You won't need to study coding too much. I don't want to give it away, but it won't be a crazy question. So you won't have to worry about it too much. You're welcome very much. So if you notice what's going on right here, you should know what all this output means. You should understand pretty well. I can tell that there were a little bit more females than males. I can see here just the distribution of females is about 55%, to the distributions of males is 45. I can see here that this is the marginal display of handedness. So we have here that something like, I don't know, 5% of people, maybe less, 4% of people are ambidextrous, 10% of people, maybe like 12, 13% of people are left-handed and right-handed. If I wanted, I can figure that out. We could just go here to table, and we'll go here to survey 10, because why take guesses? We'll see. I say 412, and then that would leave 84. And then divide by n row surveying. And then we'll wrap this all up, take this all, put it inside of a round, and then we'll round it to 4 decimals, and then we'll times by 100. Cool. I said 4 and 12, I was off, kind of close-ish, but we can get the percentages right here, and just practicing code like that. We haven't done this in a while. I'm not going to throw code at you like this. I'm not going to ask you to code that. Notice how I kind of built it. I built it from the outside. I kind of just built around it. So those are the percentages you're seeing. Let me show you again. Those numbers I just found out. This is the 3%. That's the height of this bar. The 8.73 is the height of this left bar, like if you were to just subtract off that. And then this is 88% of people are right-handed. If you can see, it's pretty obvious about 55% of people are female. So we could easily change this, and Y code is awesome. You can do that and just 55% like that. And that's just one of the things I love, where you can just change one thing and get to what you want. Like you write this nice long code, takes you a while, and then boom, change one thing and you get the other thing you're looking for. So that right there is what we call the marginal display of gender. So you can see it was pretty easy to see that's 55% female. So those are the marginal displays. But what we really care about is the inside right here, which is going to be displayed by the contingency table. So the contingency table, it's kind of a mini lecture right now for a moment. The contingency table gives us the count, as in there are 12 females who are ambidextrous. This little black box right here is 12 females. There are 11 males who are ambidextrous, and it's a little higher because there's less males. There's 30 males who are left-handed. I'm using these numbers right here, and please tell me if I'm wrong. There are 31 females who are left-handed. There are 343 females who are right-handed, and 272 males who are right-handed. Total, there are 615 right-handed people, 61 left-handed people, 23 ambidextrous people, and there are 386 females, and there are 313 males. That's what all those numbers mean right there. You notice as I hover over each part of it, the marginal display of gender, the marginal display of handedness, and the bivariate relationship that these variables have with each other. The bivariate is the inside of the contingency table. So the contingency table shows you the variables, or excuse me, it shows you the counts for each of the combinations inside of there. If you notice right here, we have the expected counts. The expected counts would be row total times column total over grand total. So any of these numbers can be found if I take, please tell me as I figure this out, 200 points first person to tell me, not handedness. If I take the row total right here, or column, you can call it whatever you want. So I do column total times row total over grand total. So tell me, I'm fine. What will this solve to? Do it in your head. You don't have to do it in your head. What will that solve to? 23 times 386 over 699 will solve to, exactly, solve to 12.7. And the reason we knew it was 12.7 is because this is the expected count for female ambidextrous. If you notice here, we're talking about this one right here. If you go to this cell, that's the count. That's the observed, how many there actually are. So going down here to the ambidextrous, we see that there are 23 ambidextrous. That's why I get that 23 right there. There are 386 female. That's the 386. So row total times column total over grand total. I wish I could annotate on the screen right now so I can do my classic, like circle the row total, circle the column total, times them together, divide by grand total. Row total times column total or grand total. Let's put a hashtag right here. Row total, put parentheses, row total times column total over grand total. So row total times column total over grand total gets you that specific expected cell count. Then the other formula we have is the discrepancies. The discrepancy, we can kind of do some of the math right here. We can take the observed minus the expected. Oops, I'm grabbing the wrong thing. Observed minus expected. And we can square it, observed minus expected squared, divided by expected. Observed minus expected squared over expected. And if you'll notice right here, what should this equal mathematically? It is on the screen. What should this equal mathematically? Observed minus expected squared over expected. And it's quantity squared. Observed. I'm going to, while you guys solve it for another 100 points, I'm going to go ahead and write the formula right here. So it's O minus E squared. So be solving it. You can solve it yourself, but I know the answer because I can see it. Observed minus expected squared over expected. What should that equal out to? Oh, we should know, or you should be able to tell me. It's on the screen. Yep. Oh wait, yeah, you might have round. No, it might, it's a rounding thing, I think. Oh, does it? Oh, is it not carrying enough decimals? Oh no, I know what it is. I think I know what it is. Let me see something real quick. Is that really? No way is that decimal doing it. No way. 0.0386. Did I take the wrong numbers? Let me double check. Observe, we observe this many females who are ambidextrous. We expect this many females who are ambidextrous. So, oh, I'm looking at the conditional distribution. You are right. Sorry, this is not the answer. Everything we've done here is accurate. It just doesn't show the cell discrepancies. So no, so Alden, sorry, my brain is breaking, guys. This is not the right answer. Maybe you guys were even noticing that. These are the conditional distributions, which means given somebody is female, what is the probability they're ambidextrous? We could figure this out in a moment if we want, but that's given someone is female, what's the probability they're ambidextrous? So you are exactly correct. This is the cell discrepancy right here. Alden, you were correct. And yes, I'm just doing all these tricks on you guys tonight. So this is the formula. It's like when you don't see the same number, you're like, wait, what went wrong? But observed minus expected squared over expected is a cell discrepancy. Then what I would do is, how many cell discrepancies would there be? How many cell discrepancies? Thank you, Alden. Yeah, it says conditional, and I'm like, oh, those numbers are decimals. This answer is probably going to be a decimal. It's funny, I do these more by hand than I look at the output, because in 201 we do this all the time. We do observe minus expected or expected. It's classic Mendel and his p-plans. So how many cell discrepancies are there? The picture kind of gives it away. How many cell discrepancies are there? I do like these. I think of all the questions I've written this one before. This one catches students off guard. How many cell discrepancies are there? You are correct, Lauren. 100 points, Lauren. You are right. 1, 2, 3, 4, 5, 6. Now think about this. You have to have observed minus expected squared over expected. You only have 1, 2, 3, 4, 5, 6 observed. The observed are these numbers inside of here. I'll highlight them. Here's your observed. Here's your observed here. These are the marginal displays right here. So they are observed, but we can't, there's no expected marginal display. We use the expected for the cells, the expected cell. So see, it even says expected counts, and they're for the cells. So here's the counts or the observed. So great job, Lauren, right there. There are 6, and then there are 6 cell discrepancies. If you want to get this number here, I haven't done that. So I shouldn't say, now I want to write the test question. So given somebody is female, what's the probability they're ambidextrous? You can take this number right here, and this is a conditional distribution here, as it says, and then that equals that 0.0308, and I'll just copy paste so we can see it in the same screen. But this number right here is given somebody is, and let's just take a look right here. Boom, same number down to the decimals, and that's all the math it's doing. It's just saying, given somebody is female, what's the probability they're ambidextrous? And yes, and let's think here. Let's run the output. Keep asking those questions if you have it. So with this right here, let's take a look at our output and let's figure out, is the relationship between gender and handedness statistically significant? Are these relationships statistically significant? No, and we know that because of the p-value. So the p-value is right here, and then is this interval conclusive? It is, and we know the interval is conclusive because the interval does not contain 0.05. So with this in mind right here, we have a test that is not significant and is conclusive. Does that make sense to everybody? I feel like you guys really have this down. I feel like there's gonna be really great grades. I guess feeling pretty good about this material. We've covered some of it so far. We're gonna go into regression now, and we're gonna do some new topics tomorrow, maybe do a little bit of review, but I won't put the new topics on the test tomorrow. So we're just gonna cover a little bit. Will there be logs on the, I haven't put a log on there yet. Why is it not statistically significant? It is not statistically significant because the p-value is above 0.05. So that right there is not statistically significant. P-value above 0.05, not statistically significant. How does this slope interpretation change? I think Christian might ask this earlier, and we'll go into this. Like, what changes in the quoted interpretation otherwise identical? That's pretty much it. we'll do a multiple interpretation here. Let's go back and so let's do that. Let's write, well, we've already got a multiple regression model. Why not take it? So let's go interpreting in regression, multiple. So here we go. Let's paste it in. Let's put the summary. And we've already ran. Okay, so try this. Please try this. I'm going to give you guys a moment. And with this, I want you to interpret the coefficient of weight. I want you to interpret the coefficient of weight. And these are individuals. We are talking about height. We are talking about weight. Interpret the coefficient of weight right here. Interpret the coefficient of weight. Be very careful. I'm gonna see how I would grade you for interpreting weight. How would you interpret weight right here? Let's see who can get the highest points. I'll throw 200 points whoever gets the highest. 50 points every answer, but who can get the best? Take your time and practice. This is your chance to be able to interpret it. So remember, one, this is a multiple regression. If you're looking what to put on your sheet, if it's a multiple regression, you do have to say, but are otherwise identical. And I accept that. I accept but are otherwise identical when you're talking about things in multiple regression. You don't have to say that, but they have the same desired weight, but at the same GPA. That's what we're saying. They're the same in every aspect, but they differ in this X by 1 unit. So we're interpreting the coefficient of weight. Who can get it first for 200 points? Trying to figure it out. This is really good practice. If you can do this right now, maybe you don't even have your cheat sheet, you are on the right track if you can do this. The intercept, I'll talk about the intercept here while people are trying to write it. The intercept really doesn't have a good interpretation. The intercept would be among individuals who have no desired weight. Their desired weight is 0. Their weight is 0, their GPA is 0, and they don't text, which is about the most logical thing we could say out of the illogical things. Who doesn't text, though? So among individuals who have 0 for all these things, desired weight, GPA, text per day, we would expect them on average to be 52 inches tall. That's what we'd expect on average among people who have these characteristics. Pretty illogical. 2 individuals who differ in height by 1 inch but are otherwise identical would be expected to differ in weight by 0.036 pounds, with the taller person expected to weigh less. There's a confusion at the end there. 2 individuals who differ in weight by 1 pound but are otherwise identical are expected to differ in height by 0.036 inches, where the individual who weighs more is expected to be shorter. Oh, that's so crazy, right? That's so crazy. It's a negative coefficient. I'm seeing some great interpretations. Everyone who interpreted this, get 200 points. Great job. I really like that you guys are practicing this. For 2 individuals who differ in their weight by 1 pound but are otherwise identical, they are expected to differ in their height by negative 0.036, and I would add in inches there, with larger weight, and that with people who weigh more expected to be shorter. I would add in just a little more clarity with larger weight being shorter, just a little more clarity where people who have a higher weight are expected to be shorter. And that's just so crazy. And this is very, very, very statistically significant. And the thing about this is, it's not saying if you weigh more, you're shorter. It's saying in this multiple world where we have all these coefficients in, 2 people who are otherwise identical, so they have the same desired weight, but one person weighs the same desired weight, same GPA, same text per day. Desired weight's the main one that's really doing the model right here. But they have everything identical, but the one person weighs more. The person who weighs more is expected to be 1 pound more, is expected to be 0.036 inches shorter. And I know 0.036 inches shorter is not that much, but that is statistically significant. It's pretty darn statistically significant. So pretty interesting stuff right here, and I really like this. If I had ran this right here, I would have used it as a test question. So this is a high candidate for a test question because it's almost confusing. I like things that are confusing, especially when you get into the multiple world. This is a little bit talk about multiple world right now. How does something, we've even said this before, how is something significant in the multiple world? How is something significant in the multiple world? It brings unique information. It brings unique information, correct. It brings new/unique information. It brings information that the other variables are not accounting for, which you can call new or unique. New means other things aren't already doing it. Unique means other things aren't already doing it. So it's synonymous words. We're pretty much saying the same thing. Great job. I think, Elijah, you cheering everyone on. I'm throwing another 100 points. Thank you. I like all the positive attitudes. Keep up the hard work. You guys are really, really I really appreciate it, and I appreciate all you guys working with each other. So right here we see that these things are. So do you think GPA is not significant in predicting someone's height? You're in for a surprise because I'm betting you. Oh no! I bet you GPA is because I know something about it. I bet you if I take this right here and I just predict height from GPA, I'd wager $10. I shouldn't wager. Simple linear regression. We'll go here. Okay, let's do this. Someone could say to me, well, wait a minute, Brian. Your model shows that text per day, or excuse me, GPA is not significant. But GPA is not significant when the other variables have already done it. When GPA has come into here, what is it not doing? GPA is not able to do what? It's not able to reduce the what? GPA is not able to reduce the what? Not uncertainty, not uncertainty. GPA, what is the whole goal to try to explain? Think about how we calculate. Oh, I erased the picture today. Oh wait, Victoria, Heather, you guys are right. Reduce the sums of squared error. Nathan, nice job. Nathan, I haven't heard from you. I'm telling you, 100 right there. Just I like you chiming in right there. Reduce the sums of squared error. Exactly right. We want to reduce the sums of squared error, and GPA is significant by itself. So what does that mean? GPA by itself has information, but what do you think that information is kind of intertwined in? That information is kind of intertwined in gender. And you know what? Gender is also, if you look here, gender, look at the variance inflation that went up. Variance inflation went up with desired weight too. So, and GPA actually didn't, wow, GPA is not, I stand corrected. Apparently GPA, well, GPA does something meaningful by itself, but it's pretty happy not being variance inflated. So I was pretty wrong that it has an entangled variation with gender. If you saw me put in gender, pretend I didn't. It's categorical variable. We haven't talked about those yet. We're not going to talk about categorical variables on this test. So I'll click the money. Wait. No, I was right. That's me being right. I was wrong on the other stuff earlier. I got them wrong, but I got this right. Yeah, Ethan's right too. That if we see that means that what GPA has is being overlapped by the other variables to some degree. And if you notice GPA, look at this R squared right here. You might say to me, well, Brian, it doesn't have much high variance inflation. But what little it does, that 2%, basically, that 2% R squared that explains, as in, I'm gonna round it, 2% of the variation in somebody's height is explained by the variation in their GPA. If you heard that interpretation, 2% of the variation in somebody's height is explained by the variation in their GPA. As opposed to our multiple regression world, where 62.25% of the variation in somebody's height is explained by the multiple regression model, as in the variation that is explained by their desired weight, GPA, and text per day, when we look at that all as a whole, like all of those. Yeah, and good point. I like that you guys are chiming in here, because that's where I was going to go next, Preston. So another 100 points to Preston. Talk about multiple world. Talk about output in multiple regression. So I want to kind of talk about that output, because when you look at the multiple regression output right here, let's focus in on some stuff. We have here the R squared, but R squared, as we talked about in class, and this is my favorite example when I talk about playing video games, of course, right? Just show some Smash Bros right here. So I can't even play it in my office because the TV won't work with it. Can you interpret R squared again? I'll do it a little slower this time. Blank percent of the variation in Y is explained by the variation in the multiple regression model. Blank percent of the variation in Y is explained by the variation in the multiple regression model. 62.25% of the variation in height is explained by the variation in the multiple regression model. I know sometimes just you can always say slow down to me. I'll slow down. I'll try. So blank percent of the variation in Y is explained by the variation in the multiple regression model. If it's a simple regression model, usually we just say the simple model. Like, you hear me say 1.895% of the variation in height, because that's my Y, is explained by the variation in GPA. 1.895% of the variation in height is explained by the variation in GPA. But when you get to the multiple world, you usually don't have time to say all the variables, so you just say the multiple model. And then it's like, oh, those variables are doing the explaining. Preston pointed out, and rightly so, that we see here that the R squared adjusted is quite fine. It's like your friend says, lunch will cost $62.25. You get there and it costs $62. Maybe I shouldn't use that example because I use that a lot for uncertainty and stuff. It's, 62% and 62.25. You notice I didn't even say that 62.03. They're basically the same. It's so small. So what is the R squared adjusted doing? And this is definitely could be on the test. R squared adjusted is when we penalize ourselves. That's the key. R squared adjusted is us penalizing ourselves for the extra variables in the model. Adjusting, I wouldn't say for the multicollinearity. It's adjusted for the advantage a model has with more variables in it. So Brian, I haven't heard from you tonight, still 100 points, thank you. It's adjusting for how many variables are in the model. It's not how the x's relate to the x though. You are kind of right, Brian. It's not literally adjusting for the multicollinearity, but models that get hurt, two things. A model that has high multicollinearity is probably going to get hurt a lot more in the R squared adjusted. But also you could have a model, this is theoretical now, you could have a model that just has bad x's, and those bad x's could not, don't explain each other well, and then the model would have a bad R squared adjusted. So yes, while we will see models hurt that have issues with multicollinearity because the x's aren't bringing with them new information, an x can fail to bring new information if it's just a horrible x. So you are correct in a lot of ways, but then there's the caveat that it's merely just adjusting for the x's in the model and kind of taking away our advantage of having more x's. Correct, Evan has it correct. Adjusting for more variables in the model more defined with R squared adjusted. Remember, there is no interpretation of R squared adjusted. It's just a much more fair assessment of how our model is doing. So when we look at the R squared adjusted, we can be like, okay, that's a more fair, grandma. That's a much fairer assessment of how our model's doing. R squared adjusted can be negative, which one of my students had on their econometrics test. It was like, R squared adjusted can be negative. And they're like, R squared can't be negative. R squared can't be negative. R squared adjusted can be negative. And we could, I don't know if I have the right variables to do that. I would need things that really don't explain each other. So I'd have to get a really bad subset of data. And it's not too hard to make a negative R squared adjusted. You just need bad variables. And a lot of good thing is some of our data sets here, let's just find something really bad and do a multiple regression model and make a negative R squared. We'll do, a lot of these are intertwined with gender, like piercings is, so we don't want to do anything like that. Distance moved to school, cool. It's gonna, if it has anything good, then R squared adjusted won't be negative probably. Let me just take out the good stuff. Yeah, there we go, negative R squared adjusted, first try. So I just tried to make a model that was just pretty bad and didn't explain anything. And so my R squared's bad, and when I adjust for how bad my variables are, we can also check this right here for variance inflation and probably won't have any. Yeah, variance inflation is not a problem. So it's just horrible R squareds. Why need to be fair and fair compared to what? Yeah, that's what it is basically. It's a way to assess, here's the thing, Lucas, and you bring up a good point. Every time we add in x's, your R squared will do what? Every time I add in an x, my R squared will do what? It'll go up. It'll go up. So, and so, yeah, we'll do that right there. And so I'll do that very next, Lauren. Great question too. So since we know R squared will always go up, R squared will always go up. It's not really fair for us to compare two models by R squared and be like, okay, this model's better because it has a higher R squared. So in the multiple world, you use R squared adjusted for model comparison. So someone might say to you, which of your models has the highest R squared adjusted? Because then if a model has needless variables put in it, then it'll have a lower R squared adjusted. So how do you tell which of your model is better, which model is better in the multiple world? R squared adjusted. That's one way. The other way, 100-point bounty on this one, it is on the screen this time, it is. 100-point bounty, what other metric can we use in the multiple world to figure out if our model is better than another model? It's another one that is adjusted for how many variables in the model. And I'll interpret it right after that. So just in the interest of time, I might get the answer here. Not the, careful. Yeah, RSE, you are correct. RMSE or RSE. It says RSE in the output, which is the residual standard error, and that's the uncertainty in my prediction of Y. And I'll do the F-stat and I'll do the VIF here next. The residual standard error, also known as the root mean square error. And once again, when you think root mean square error, remember that root and square cancel. So those cancel right here. Let's write that in a hashtag. Root and square cancel. You're left with mean error. So it's your typical miss. When you think root mean square error, you have to do it mathematically that way. I won't get into that. But besides the math, you think about it, it cancels, and it's basically the typical miss your model makes. And since we've rooted it, it's a plus or minus. So it's like you typically miss by about this much. And so you can kind of estimate it. Let's see here. I'll show you. Well, I'm cheating if I look at it right there, right? Actually, let me do one I haven't cheated on. Let's go to weight. And, okay, I'm not going to look at it. It wasn't output prior, but I promise I'm not cheating. Okay, so when you look at this model right here, does everyone see this boundary right here? And it goes, this line hits at about 61, and this goes to 69. I won't put this on the test. But if you think about this interval, which is the prediction interval for an individual, kind of touching on that right now, and we'll go back and do the interpretations in a second. I would guess that the root mean square error for this model, which is not on the screen, is about 3 or 4. I'm going to say 3.6. And we can make the model right here. And here it is right here. How did I know that? And I was pretty right. Maybe I saw it earlier, maybe I didn't. But remember I said, this is about 61, this is about 69. 61 to 69 is a width of what? It's a width of 8. And the prediction interval is about how many standard errors? 2 standard errors. What's 8 divided by 2? 4. And so that's where I'm coming up with it right there. Remember, it's our uncertainty. So if you go out 2 uncertainties, you'd contain about 95% of the observations, i.e. a 95% prediction interval. So that's how I'm kind of visualizing it right there. It's like 2 uncertainties around the line. So when you think if your root mean square error is higher, it's going to make these prediction intervals wider. And we don't want that. We don't want this higher uncertainty. So interpret this right here. The typical miss I make when predicting somebody's height is about 3.554 inches. The typical miss I make when predicting somebody's height is about 3.554 inches on average. Doesn't matter, say on average. The F statistic is as follows. It's a humongous F. So this F statistic here reads as follows. The amount of variation I explain versus what I would expect due to random chance is 394.2 times more. Or I explain 394.2 times more variation than I would expect than due to random chance. So remember, the F ratio is, let's write this right here, F ratios or F statistics are, let's put F statistics. F statistics are observed divided by expected. So that's kind of the way we use it right here. There's more ways to calculate them, but like when we talk about the actual math, when we go to the interpretation in the business world, we would say this model explains about 394.2 times more variation than I would expect due to random chance. So we observe it doing this much more than we would expect. And of course, you can do the whole calculations of it in the background with the ANOVA. And let's just view an ANOVA right here. I have written most of the test, but as I'm doing this, I keep thinking of more questions. So if you look at the ANOVA right here, the ANOVA actually is the calculation. If you're wondering where that 394.2 comes from, it would merely be these numbers right here. I'm not beyond putting an ANOVA table on the test and maybe blanking something out. It's pretty quick and easy to grade and pretty quick and easy to also answer if you know how to get this. I would not have you calculate this number, this number, this number, this number. You would not calculate these 4 numbers right here that I'm highlighting as I go through. This is how many variables are in your model. This is 1 minus the variables and the amount of observations. I would not have you calculate that though. This is the sums of squares accounted for by your x variables. Now, does that sound good? The sums of squares accounted for by your x variable. That's the sums of squares accounted for. Does that sound good? It should. We want to account for error. So this is the sums of squares accounted for. This is the sums of squares not accounted for. So that is our error. If we take this right here, what will this equal? what is this mathematically going to find me right here? I'm taking the variation I've accounted for and the variation I have not accounted for and adding them together. I have what I've explained and not explained. You're right. Nice job, Laura. Another 100 points. Keep up those answers coming. So now I'm going to take the sums of squares total, and I'm going to first take this right here, which is what I've explained. What did I just mathematically find right here? What did I just mathematically find by doing what I've explained over the total there is to explain? I've done what I've explained over the total there is to explain. No one say yeah, another 100 points. That's not the F. It's percent explained. It's the percent of variation we've explained. I've explained 497 point, oh my God, 4,979. There we go, R squared. This is the R squared. 36.12. Just to confirm, I'll run these outputs back to back so you can see. There it is right there, 36.0. Sorry guys, I've got another model in there. 2 seconds. Summary, MSLR. There we go. There we go. 36 point, you notice my answer is more exact because I used it. So the naive model, and good thing people are bringing up these questions. The naive model would be the flat line. I don't think I can append on a line through this. Oh, Dr. Petrie, will your thing let me do this? This will be amazing. Visualize model. I'm gonna try to draw this. I've definitely put this on the test before. AB line, H equals mean of survey. I can do this another way if this doesn't like this. I'm gonna draw in the naive model. And will this work? It worked. That is amazing. I didn't know I could do that. So now we're gonna make it purple. Or not, gotta do it in quotes, purple. And then we're gonna add in line width. What is the function for line width? That's not it. Oh my gosh, how do I know that thing off the top of my head? It's called doing this way too much. Okay, cool. We can now see the naive model plotted through here. So that's the naive model right there. It's the mean of y. It's just a flat line. The mean of y does a horrible job. And how did I find the mean of y? I literally put into my code, if you see the code down below right now, I literally said make a horizontal line on here. I appended code, which means it's just going to run them both as one line. So I appended on here a line that added in the mean of y. I made it purple because I like purple. And then I increased the line width. So I'm using a lot of ggplot. I can't believe I remembered the base R function for plot. Random thing. Didn't want to go to question mark. But that's got it. Does that make sense why this is the naive model right here? The naive model, what is the sums of squares from the naive model? It'd be this right here. So this is the sums of squares total. Like if you use the naive model and calculated the error from the naive model, then you would get 13,783. The error from the red line is much smaller. The error from the red line is this number right here. That's the error from the model. Made a mistake. That is how much the model has accounted for. This is the error from the model. So once again, let's look at the ANOVA output, and please ask any questions, and sorry if I fumble over my words for a half second. This is how much we've accounted for with our model. That is how much the X variable has accounted for. Residuals are a bad thing. Residuals are what we have not explained, as in the total variation left unexplained. So if you add up these both together here, you get the sums of squares total, which is the total error for the what model again? It's the total error. The sums of squares total is the error from the naive model. You're exactly right. That's the error from the naive model. So if we were to make squares with all these, that would be the addition of both of these. But the error from the red line is this. The red line has reduced it by this much. That's the sums of squares reduction, which is a good thing. If you notice, it's basically like 4 over 12, which is a third. That's why your R squared comes out to basically a third. It's not exactly, but 4 over 12 is that. Residual equals actual minus predicted. You're exactly right. I think put some on the test about that. If you notice here, one of the biggest residuals is this one. It's got a residual of about 13. You can kind of see it here. You can just look at this and be like, okay, that's got a residual of 13. Ooh, look at that one. 54, and it goes to about 72 or something. That one's got a residual of about negative 18. Anything on the line has a residual of 0. Anything above the line has a positive residual. Below the line has a negative residual. Further it is away, you can just take that line, make it flat, make your residual plot. Oh, you know what we haven't done? We got tons of time. You guys know what I want to do next, right? Talking about that residual plot. This gets me jazzed. I'm gonna grab a Coca-Cola here between our review and the next review. But you guys know it's time for some check regression. I feel like it's the word of the day, and everyone's gonna be like, "Woo, check regression!" Let's look at that check regression, see what we got going on here. First thing, step number 1. What do we do when we do check regression? What is our first step with check regression? Let me put timestamp. I looked at it and I didn't do it. P-values, you guys are right. They are all 0. Uh-oh, basically all 0. Oh no, check regression review, $sign check regression review. Check regression, 6 at 20. Okay, they are all looking pretty bad there, aren't they? So, I mean, fail, 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 fail. And just once again, make sure you realize that the conditions are like null is linearity. That's just an example. So if you think classical, everyone's like, why is a low p-value bad? Well, when the p-value is low, reject the null. The null is that this is linear. I reject that this is linear. So I'm saying, I don't think there's a linear relationship. And we'll see that here in a moment. I think this is the one I use correlation on also. Preston, another 100 points. One high one, you are right. Thank you, Preston. And thank you for always doing that, always answering those questions. So step 1, look to see if the p-values are low, and that's a problem. Step 2, which don't say pass or fail here. Step 2, which means we get to continue, is we look at what? Exactly, if it's a good sample size, we can continue, which means we have enough sample size to actually to look at the plots. And people have asked me, why? Why don't you just, we fail the test, we're done. It's because these tests get overly significant, overly powerful. Power relates to your sample size. The more sample size you have, the more power you have. And basically, all models are wrong, but some are useful. So our model's wrong, and we'll find that out if we have a large enough sample size. We'll fail it. If you have a model with like 1,000 data points, if you pass all the assumptions, I'd be like, wow, how in the world did you pass the assumptions with your 1,000 sample size? And then we'd have to look to see if your model is actually like meaningful to us in other ways. So once again, step 1, look at those p-values. P-values look to be low. That's a problem. Step 2, see if your sample size is greater than 25, and if it is, you can continue. And we do have a greater than or equal to 25. I'll never make it 25. Don't worry. I don't like putting it right on the numbers. So we can continue. If you're looking where that's at right there. We can continue. Step 3 is to look at the plots. What is the least of your concerns? And the output's kind of giving it away too. What is the least of your concerns? You can write my favorite word again. I mean, I see it to a certain degree, but it's not the biggest concern of mine. Probably the least of my concerns would be that heteroscedasticity. That's the least of my concerns. I might even give that a B. I mean, I do. Heteroscedasticity, you should draw around it. That's the way I was always trained to do it, and you should see it's kind of the bigger issue. Does everyone see how there's some nonlinearity to this? And maybe I'll do some of I'll do a little bit of the take home today, and I'll do some of the bonus here at the end. So we're doing the other wind down points, but heteroscedasticity is the least of my concern. Interesting enough, it has a super low p-value, but not quite 0. Close. And actually, these are never 0. They're just rounded to 0 because they're so small. P-values are between 0 and 1. Getting a p-value of 0 is like, if you actually estimate it well enough, it'll be virtually impossible, but never really impossible. Because 1, we observed our results, so our results are possible. So right here, I see some nonlinearity. Does everyone see if I were to go through the center of these points, there's nonlinearity here. So you should try to go between all these points, which the model looks good till about here-ish, and then it starts to bend down because we want to go through the center of the points, and that's not good. So I'm giving this linearity a D. I almost want to give it a D minus. It showed up and put some answers on the exam, and I'm like, ugh. I'm like debating if I should fail it. Like, it's really close. I don't like it. This right here, I might give this a D plus. I know the other one earlier I said like a C. It seems to be a little worse than that other one I saw. It's got a little more of a trail at the end. It starts a little bit later. Yeah, D plus I think is pretty consistent with the grading I gave earlier. Remember, I like to grade these things. I like to be very clear because I think grading scales are a lot better than good, bad. So the least of my concerns is the heteroscedasticity. It gets a B. the linearity, as denoted by at the higher predicted values, we start to see some sort of downward nonlinear trend. So I'm going to give that a D minus, barely letting it pass. Over here, I'd give it a D plus, maybe C minus, because I do see some sort of tail. I'm still a little unhappy about this one over here. Major concern, nonlinearity. Second major concern, non-normality of residuals. If you notice, I talked about the linearity with this plot. I talked about the normality of residuals with this plot. And then over here, we talked about the linearity with this plot, talked about the equal spread with this plot. And here I talked about the normality of residuals. So first plot, you talk about your two conditions. Heteroscedasticity, that's a great question, Alden. You've been mentioning a lot of great stuff tonight. I'm throwing another 100 points. Outliers is kind of its own thing, and outliers can really wreck stuff. I wouldn't say a relationship is heteroscedastic because of one outlier, but outliers, as we've talked about in our class, can really destroy or create a relationship that does not truly is indicative of the whole. So we have to watch out for outliers. That's kind of its own thing. Outliers are kind of like, if you see bad outliers, it can be something like, I don't know if we should use this because either we've underestimated or overestimated the strength of our relationship based on an outlier. So great thing to bring up, which we could also look at. And it's hard to tell, is that a symptom of the shift in the shape of the model, or is that an outlier? It's hard to tell, but there's problems. If I were to use this, I would use it with strong reservations. So this is not a great model. Once again, let's look at our check regression for our multiple model world. Check regression in the multiple world. All you get different in the multiple model. Cool. Oh, it's making all my plots. Or I didn't do the x equal true this time. Oh, wow. Did I? Oh. Oh, oh no. Oh, no. Oh, this is our bad model, right? Oh, that's kind of cool because this model, I kind of like it. Reason being is if you look at what we got over here, it's kind of cool. Oh man, how did the equal spread not go haywire on this? I don't know how the equal spread didn't go crazy. Huh. Wow, that's shocker to me. We passed the equal spread looking at that plot. But what is even worse? Do you guys see it? This is just like the sore thumb of this output. This is just like, wow. It's one of the worst I've seen. Like if I showed you this right here for means or medians, which that's the way I like to write those questions, what would you use? What would you do if you saw this for means or medians? Because we're not analyzing means or medians right now. We're seeing if the outliers, I mean, if the data looks normal, medians then cry. That's so horrible. That is not normal at all. That is a very right skew. And we talked about how when it's kind of pushed to the right, it has a right skew. When it's pushed to the left, it has left skew. You can see some bimodality if it's got like a bend through it. So I know p-value of 1 for the overall model, that is slicing through. But if you remember, this was our model that did horrible. Going back to that output, even though we pass, this model right here, it passes those, but the model is absolutely horrible. This model passes most of the check regression. I'd have two reasons to toss it. One, the model is just junk. Nothing in the model is significant, which you can have, interestingly enough, nothing in the model is significant and the model is significant. This is the significance of the model. The model is horribly insignificant. None of the variables are significant. Not a major concern. It's more of a concern that the model itself is not significant. And you see here that the R squared is just horrible. And then the adjusted R squared is more horrible, and it really accounts for it. The typical miss we make is 318. What are we predicting again? We are predicting distance moved from school. So it's ridiculous. Like when I predict how far somebody moved to come to UT, I'm gonna generally be off by about 320 miles. Okay, wait. I'm gonna pick a random person right here. Hopefully, Alden. I'm gonna say you moved 60 miles to come to UT. Am I right? How close am I? I'm gonna say Alden moved 60 miles. 60 miles. We'll see how right it was. I feel like I can do a better job than this model. Watch him if came all the way from California. I'll be so 180. I was off by 120. I'm way better than this model. Well, it's horrible. I don't know. We could see how Brian does it just randomly guessing, but this model's horrible. So really, when you look at this model, one, the model is not statistically significant, so practical significance just tossed out right there. Thank you, Alden. Another 100. You get 180 for that, Alden. Should have just said how many miles you moved. You told me you moved 1,000 miles or from across the globe. So here, when we look at these assumptions, these are not the assumptions. I'm just going to look at a second here. So these are not the p-values for the model itself, like the variables in the model. These are the p-values if we pass the assumptions. I want to make that very clear because a lot of people make these mistakes. Please look at this output right here. Does everyone see that output? Those are the p-values to check the assumptions in the multiple regression model. These are the p-values to check the significance of the coefficients in the multiple regression model. And I'll repeat that again. These are the p-values to check the conditions in the multiple regression model, as in, is the relationship with number of body piercings linear enough? And the answer is yes. Down here, is number of body piercings significant in the multiple regression model? No. And be careful, you notice how they both have similar p-values, but what I'm saying about them is different because in check regression, we're checking the conditions of the regression. And then in the summary, we're looking at the summary, which includes the coefficients. Did that help one or two people disambiguify the two concepts right here? Because I'll have a lot of people who get to this output and they'll be like, number of body piercings is not, Lauren, thank you, yes it did. I'm glad to hear that. Because I have people go to this output and be like, number of body piercings is not significant in the model. No, we're saying that we have a linear relationship. We checked the regression. So be careful. This is testing the assumption of linearity. And down here, we're looking at the coefficients just to bring them up side by side. And I feel like we should do a weekly review of output or something. I don't have time for that right now, though. I feel like we should do a weekly review of output. We kind of do it in class. I know, Lauren, we'll try to do more. Maybe I'll try to have one or two more review sessions. I hope this is helping you guys. Let's do this. Let's grab this simple linear model here, and I'll show you guys something to help you with the take-home. So be working on your take-home. Do not turn in your take-home late. I'm going to do the process of one of your questions right here. I think there'll be 3 bonus questions. I think there's 3 bonus questions. I'll talk more on it in class. But yes to weekly app interpretation. I need to make videos. I need to make videos for 320. And then I can be like, watch this video on how to interpret this output. And I'd make the output and interpret it like I do with my tool on videos. And then I think that'd really help you guys. So gotta sit down, gotta make more videos. So, okay, let's look at this right here. I think there'll be 3 bonuses. What I think it'll be is you can get up to 105 on the take home. Each of the bonuses will be worth 2 points, and you can get the 3 bonuses. Now, each of the other questions will probably be worth, I think, 11 points or so, because I think that'll make 9 questions. So even the question of what is your UTID number will be a point or 11 points. But your grade, the big thing to worry about, the big thing to worry about will not be the bonus questions. If you get every bonus questions, they can be worth up to how many points? So let's kind of review, and I'll talk more about this in class, and I'll have everything hashed out tomorrow completely. All the bonus questions, you could get a total of, because there will be 3, each worth 2, you could get 6 points. I'm basically going to work one of them right now. But you can make up to 105. I like 105 rather than 106. So you can make up to 105 on the take home. But if you were to miss 1 question and get all the bonuses, what would you make on the test? Basically a what? I think a 95. So you can see right here, you would get 8 out of 9. 8 out of 9 is that. And then we would add to that, let's put this in a parentheses here. I'll just wrap it. And then we'll add to that basically a 95. So that's what you'd get right there. You can see the different grades you would get. This is with getting all the bonus. But here's the thing. If you look at the difference, if you don't get the bonus, I mean, the biggest thing is worry about the stuff we've done. So does that make sense? Like, focus in on the stuff we've done. Worry about the questions that you know we've covered, not the ones I'm about to do. And this question is not hard. I know Preston and I were doing the extrapolation check earlier. I was at least explaining, because I'll explain the bonus a lot more. Maybe I'll mention some in class tomorrow. But when it comes to the bonus ones, I'm a little more lenient on what I'll tell you guys. But with that in mind, I'm not going to give away the answer. But if you guys are like, how do we do the extrapolation check? I'll kind of explain briefly, which I could do an extrapolation check on this one too. Why not? Okay, so let's do the choose order, which is some fun output. I really love this. So does everyone see the choose order just takes your model You put in your model, and it makes the following output. Now, I want to explain what this output's doing. This output right here is showing you your linear model and all the polynomial models. Is that your ID? Are you serious? Oh, okay. It should be fine. Just make sure to keep everything. It'll show you when you make your exam. Just make sure whatever you put into the sheet, it actually will make the same exam. Do I have that up? I don't know if I have make exam on here. I don't think I. If you enter in like something like, just talking about making the exam real quickly, briefly here. If you enter in this, or you enter in this right here, it'll just delete those zeros. So it won't change it. Don't delete whatever you enter in as your ID. Enter in, like when you run, I don't have it up here, but if I were to run make midterm, like let's pretend I had it in here. If I enter this in right here, then I would enter that right there. And when I get to the Google Sheet, I would enter that in. Now I know I said the zeros don't matter, but I'd still just enter it in. Because when I make your answers to this, then it's literally going to take this and run it. It's going to run it exactly the way you ran it. And if you notice, if you rerun make your midterm, it'll make the exact same midterm with the exact same data. And so when it makes the midterm, if you watch my video, and so do follow the video, I know I was talking to Preston about it a little bit, and he did it perfectly. Take everything, even where it says like you entered this as your ID. And if you put in a wrong number, either regenerate or tell me, but make sure you keep your output. Keep your output, because I have had 1 or 2 students have lost it or been like, I entered in a wrong number and I don't know what it is. And they're like, just put whatever whatever you put in right there, just put it in. It should be fine. Like this should be the same results as this right here. This should be the same result. So, but whatever I enter in there, I would just enter in. And if you feel like there's an inconsistency, talk to me, but that's never been the issue of zeros or not zeros. It does the same thing. It's the same number mathematically, so it does the same sort of seed. So that shouldn't be a problem. But I would just, if I wrote this, I would copy paste that into my Google Sheet. If I wrote this, I would copy paste that into my Google Sheet. Like copy paste what you do. Don't try to write it. Just take number, copy number, paste number. So with this right here, let's go ahead and let's take a look at the choose order function. Okay, so let's put right here a timestamp on this. 6:35. Let's do this. Talking about take-home midterm. 6:33. Doesn't the highest the order of the, okay, so Evan, here I'll explain real quickly. Here's the way to do it. This is the way I'll cover it when we do it in class, and this is, expect this more to be conceptually on the final. This won't be on the midterm conceptually. I'm not gonna put a conceptual on this on the midterm, and this is bonus on the take-home right now. Step 1, so I have steps, of course, right? Great way to learn stuff. I do mean that actually. Step 1 is to find the highest R squared adjusted. Which of these is the highest R squared adjusted? So which of these is the highest R squared adjusted? It is order number 6. So I'm gonna grab here order number 6, and then I'm subtract from it 0.005. So if you notice here, I subtracted 0.005. So what I'm gonna do here is I can use, and this is the way a lot of my students do it, is what you should do now is you should start with the simplest model, and this is your requirement. You need to have an R squared adjusted of at least 43.01. Can you use your first model? Does that have an R squared adjusted that meets your requirement? I'll do another one here in a second. Does that meet your requirement there? Yes or no? And look at the R squared adjusted. Does that meet my requirement? That I need at least this? No. How about second one? Does that meet it? Third one? Fourth one? Does that meet my requirement? Is it at least that? There might have been a delayed no on that last one. This does meet it as far as I can see if my eyes don't deceive me. So with this in mind, let's do another one. I'll explain briefly the process again. Here's the thing, and I'll explain why we're doing this. This goes kind of the idea of R squared adjusted. We want to use simpler models. Imagine if I could get to New York, like 98% of New York, and I could take one plane to get 98% of the way to New York. Or I could take 10 planes and get 99% of the way to New York. Which of those sounds like a better trip to New York to you? One plane bringing you 98% of the way, or 10 planes bringing you 99%? But wait, that one plane's not bringing you as far. Do you see how we kind of like simpler things in this world? You're like, wait, one plane brings you 98%, 10 planes bring you 99. Why would we use 10 planes to get that one extra percent? So what we're doing right here is we're saying, even with the R-squared adjusted, we're kind of using a cutoff. This 0.005 is a metric that Dr. Petrie uses. All in another 100, making me laugh. I like that. Avoiding Newark, New Jersey. So I've flown to Newark quite a few times. Good old Jersey. Uncle from Jersey. He passed. He's all right. But Jersey, he is. Whew. You know, they had that show Jersey Shore. They probably still do. Ooh, that show Jersey Shore. Let's go grab another variable right here. Okay, so we're going to put in GPA here. We're going to explain height with GPA. I'm going to go to the choose order function, and let's repeat the process to make sure we understand how to do this. This one, if you look at the output, you can see it. If you look at the models too, you can see it. Does anyone see where the highest R-squared is? Where's the highest R-squared adjusted? Step one is to find the highest R-squared adjusted. I'm going to ask a different question right after that again. Step one is to find the highest R-squared adjusted. We're going to go for about 6 more minutes because I'm going to try to grab a Coca-Cola between this and my next review. Doing a review from 7 to 9 for the next class. Substitute top this morning. No, I've lost you guys. What is our highest R-squared adjusted? Order number 3, you are right. Thank you guys very much. Order number 3. This one right here is our highest one. What are the only models we will consider now? I'm asking it in a different way this time to kind of teach it a few ways to make sure we get it down. What are the only models up for consideration? What are the only models up for consideration right now? 1, 2, and 3. So you could say we could, Preston, I think you're right too. If you say like, well, we are considering 3 right now, so 1 and 2 are additionally up for consideration. So 1, 2, and 3 are up for consideration. We could use 1, 2, or 3. Those are, it's like, okay, these are the ones. It should be pretty obvious. We're not going to use model what. Like I can see it right now. We're not going to use model what. If you look, the R-squared adjusted on this is so much lower. We're not going to use model 1. So we'll use, we'll go right here. We'll grab the highest one, and we'll subtract from it 0.005, and that gives us 0.034. Does model 1 meet our criteria? Does model 1 meet the criteria of being above our cutoff of what we want from R-squared adjusted? We want at least 0.0347. Does model 2 meet our criteria? Yep. And if you look, do you see how a lot of these models look similar? Like the black line sticks out, but the other ones are kind of similar because all their R-squared adjusteds are kind of similar. So we're not really helping that much. It looks like the second order gives a little bit of a bend, which we've needed. So let's go here to, let me get the variables back again. Let me go down here and go glimpse. I do love the glimpse function. It is such, not glimpse, glimpse. And glimpse is such a neat little thing that they made. It's cool because you can go here and go to like weekly hour video games. Go here and GPA and weekly hour video games. Let's switch those two. It makes more sense to say, we'll end talking about some video games here and we'll do extrapolation check. I might actually need them in reverse. Well, I do it that way. None of the, this is an interesting one. Highest one is this one. These are just bad models though. None of these models, this is not a good model. We went from bad to worse. But you would use that model. I'm going to go above what we know for a second. I'm actually going to look at the model. Okay, let's go ahead and actually make that. This is advanced look. So let's do this. Let's put this inside of a poly. What am I using? I'm using order 5 on it. So poly, there we go. And then this is not something you know yet. Do not worry about it. See, there's the R-squared adjusted of 13.88, and that's where that came from right here. There's something to it, but it's just pretty bad in general. It's a bendy, crazy model. It explains 2%. I don't know. See how the 5th order is actually significant? Don't worry, we haven't done poly models, but that's how you add a poly. Oh, good. We'll show this too. If you're looking to add an interaction, which is also a bonus question, do you want to add an interaction to your model? Just do that. And let's do summary. I'm just throwing some major, I might even show every bonus. If you want to add an interaction and view the interaction, Preston, I think Preston might know where's the coefficient for the interaction, or where is the, like what is the coefficient of the interaction term in this model? We have not covered interactions and how to interpret them yet. So they're a little crazier. If you do the visualize now, you'll get a very different output. I'm just literally burning through. Yeah, exactly. Look for the colon right here. This is the interaction term. You can actually do a model with just the interaction if you want. There's a model with just the interaction. I wouldn't suggest that. We'll talk about model hierarchy later on, but that'll be a term you'll hear later is model hierarchy. Last but not least, you're like, Brian, slow down, slow down. I'm literally trying to show you anything else I can show you here. Let's do new data. I'm gonna use this model right here. So I'm gonna do extrapolation checks. That way we can see when I need that one. That's easier to type. Okay. Extrapolate new data, data.frame, and then GPA equals 40. You'll see why I did this. Extrapolation check. Oh, need to look at that now. Multiple simple linear model and new data equals new data. Should do my extrapolation check. It's not liking it for the moment. We will just ignore this here for the moment. What's it not liking about this? Is my model not, let's see here, summary. I might ignore the extrapolation check for the moment. It's being very unhappy with me. GPA, and let's see here. Does the extrapolation check only work in the multiple world? Oh, I think it does. Well, that's fun. Let's do that. Weight equals 200. There we go. Well, that's using the multiple now, and it needs a multiple. So cool, and it did it. I know I'm flying, guys. I'm sorry. Cool, that's not extrapolation. I'll talk more about extrapolation check as we get into these multiple regression concerns, but the extrapolation check does not work on simple linear models, because if something's an extrapolation in the simple world, it's easier to see. Does everyone see right here where we would do an extrapolation in this simple world? Where would extrapolation begin and end on this simple world for this model? Outside of where and where? Where is extrapolation? Where is that extrapolation? And this will be like our last few questions. No, lost everybody. I'm gonna grab my wallet. Where is extrapolation? Oh no, is everyone gone? I can't even see. Extrapolation would begin anywhere outside of 0 and 40, about, yeah, whatever this highest point is, I'd probably say about 45. So that's where extrapolation is, anything outside of 0 and 40. But in the multiple regression world, extrapolation is based on outside of like the cloud of your x's. So it's a different world with multiple regression worlds. So you have to have some way to figure out how far somebody is from kind of like the center point of all the x's. So it's a different concept for a different idea, and that's what the extrapolation check is used for. But that's got it. I'm gonna run right now because I'm gonna start getting myself a drink real quick, and email me those questions. You guys feel like you learned something tonight? Did this help? Do we know what's going on? I hope. I know I flew through the last 10, 15 minutes. I just wanted to show you guys some stuff here. I will upload this. So hopefully, I'm glad this helped. So good seeing you guys tonight. Email me those questions. We do have class tomorrow, so we will do some review tomorrow. We'll do a little bit of new topics. Won't be on the test, but a little bit of new topics. And thank you guys for being here. Thank you guys for chatting. It keeps me going. I'm going to go grab a drink, which is going to be my dinner. Buy some candy too. Have a good night, guys, and I'll see you later. I'm going to end the meeting for all, and it might kick you. I don't know what it's going to do. End the meeting. So if it kicks you, it's all right. Don't worry. And then I'm going to start the meeting later again. Bye, guys. End meeting. End meeting. Stop share. Oh, it doesn't have it. End meeting.